And yeah, today I'm here for the first time at this cluster, so I'm happy to have this opportunity to present some of the technologies that we apply. We are a young company. Pointly is a spin-off from Supper and Supper, a data science consulting company. So that's where our background is in data science and training AI models. And we are specialized on the processing and applying of AI models on 3D point clouds. I want to share a quick quote from one of our partners, and he once said 90% of our clients don't want the point clouds. And that quote really stuck with me because that partner, they are producing laser scanners, which are essentially creating 3D point clouds. So of course you want to wonder what do they want if they do not want the point clouds. In the end, point clouds are just a vehicle to create further data products like digital elevation models, tree inventories, or any kind of 3D models, map layers, or meshes. And point clouds themselves, they are quite a bulky format, very compute intensive, not easy to handle. So we have large amounts of data with high precision, but we actually just want to extract further information from them typically. So that is something that we have taken ourselves as our task to do. And we have built a cloud platform to support this process. I want to talk a bit about the platform and quickly show some examples of how it can be used. And also then tell a bit more about how we train our AI models and do the classification and vectorization on the point clouds. So the key features to extract data from the initial point clouds for us are classification and vectorization. I will mainly focus on classification in my presentation today, but yeah, maybe first showing two short videos to demonstrate what this looks like. So the classification is something that we can also do on the platform manually. So here you see a quick video showing how classification is done with some segment-based approach. So we have different classification tools. We can draw polygons. We can create 3D bounding boxes to do classification. So those are like the classical segmentation tools. But we also have this cluster approach where we can quickly, like with a magic wand, click on an object and a big part of a project will be classified. So it really speeds up this manual classification workflow. The second part on the right side is the vectorization. That's actually a different approach. We can add point features, we can draw polygons around objects, and we can draw polylines. So this is a different approach. We add another layer on top of the point cloud. We do not directly work with points as for the classification, but we create new features which can be exported as their own dimension or data type and can be imported into other tools immediately. And vectors are a very lightweight format in comparison to point clouds, and they can also carry a lot of metadata information like type, length, and a lot of those attributes can be added to each of the vector elements. And now you're wondering what we do as an AI company. Of course, we are going for deep learning automation of those tasks. We have built the platform to also support the manual processes because we need to create training data as well, or sometimes you need to do some amendments. So all of that is possible manually, but our focus is on the automation. And there are many different use cases where we can apply this technology. So I already mentioned like airborne laser scans is like a very typical application. So we work a lot with this kind of data taken by planes on large areas, but we also work with mobile mapping. For example, highways, we have many kilometers of highways all over Europe. We have city inventories where we can mount a laser sensor to a car, drive along the city to detect all the assets around, like street signs, street lights, trees, also the streets themselves, or street markings are also common use case. Of course, on railways, this is also more and more common to mount laser scanners to a train and drive along the tracks to create a digital representation of the tracks. I will show more about that later on. And another common use case are power lines. So you can use either planes, helicopters, or drones to fly along power line paths to very precisely classify the pole positions and the wires, and then extract that as a 3D model and do some load analysis, for example, and yeah, really create a kind of digital representation of your point clouds or of your assets by that. And yeah, what we have done for some of those use cases is to train standard classifiers. So for like 3 of the use cases that we see here, airborne laser scans for the highways and city inventories, we have trained our own standard classifiers. So the pre-trained models that we can use as baseline models for our projects. And they really kickstart then a project. If we work on a project for airborne laser scans, for example, we can use this classifier to pre-classify data and then optimize that for a specific project and yeah, create a new optimized workflow for a new client or even a new use case which just has a similar data type. So it helps a lot to have some available models, which we also offer on the platform for all our users. But then within our projects, which I want to show now, we also train custom models for new use cases, and we add further analysis steps within that classification workflow to also extract features to create the final data products that our clients need. And to cover also a bit like the approach that we're using, it's and why we have this cloud platform for that. Within the cloud platform, we can cover the whole data science or AI model life cycle. So from the initial training data generation, which I've shown in the very beginning, we can do the manual classification to train or show the classifier how objects look like and how they should be classified. So that's just the beginning. We can then train the initial classifier, deploy it on the platform, and apply this model to new data. And then we see where we still need to optimize. We can correct any misclassifications of this initial classifier and iteratively retrain the model, deploy it again. And all of that is supported within the platform. And we can even then deploy the final model and apply it to very large scale data sets. So we have this kind of workflow which is really optimized for the use case 3D point cloud classification. We have a lot of freedom to customize parts of that pipeline, and by that we can do the projects very efficiently. Now to show some of the projects, and I want to start off with 2 projects that we did for the British Ordnance Survey. First one is a bit special. It's not even laser scanning, because I also wanted to show that the LiDAR sensors or laser scanners are not the only use case that can be covered. This data is photogrammetric. That means it's derived from 2D imagery. This is based on aerial images, which are then stitched together in a so-called photogrammetric process to identify 3D objects. It's a bit similar to what you see on Google Maps if you switch on the 3D mode, but this is rather the raw data, and we can also train AI models on that. So here we do not have so-called intensity values, but we can use the RGB values for training as well as any near-infrared if it's available, and also detect objects like the vegetation, building roofs. We have in yellow the roof clutter here, any objects on the roof, building facades, vehicles, and so on. So all of that is possible, and we can adapt our pipelines to work with any kind of input data that we have, as long as it's a 3D point cloud and we want to do the segmentation task. Second project with Ordnance Survey was for mobile mapping. So here was the goal to see how far can we get, how good accuracies can we reach with a medium-ranged laser scanner. So this is not a high-end model, but rather a mid-range one. And for this mobile mapping within the cities, we want to remove those kind of vehicle artifacts. We see all the yellow points here, which are caused by vehicles driving behind or in front of the scanning vehicle. So we want to remove that, clean the point cloud. We also want to detect parking vehicles, which can also be removed when, or we want to detect, of course, the assets in the street, like the street lights, signs, and further objects. Now about some of the airborne laser scan projects. So as I mentioned, the goal is to offer a scalable platform that really works with large data sets. So City of Munich was one of those projects where we classified more than 500 square kilometers. And you might know that within a large, big city, we have so many different kind of objects. So we need to do a very good selection of training data, try to show many different areas. For example, train stations are very, very complex. So we included some of those in the training data set. We included some construction sites because they also look different every time. And we try to make the model as robust as possible for even for the edge cases. So we do the training data selection, retrain the model based on our standard classifier, of course. So we do not start from zero for such a project, but we then add more edge cases in the training data set to make the model more robust. And once we have done that, we can apply the classifier to the whole data set. And in this case, like typically we tile the data set. We do not work with one 500 square kilometer file, but we do like 1 by 1 kilometer tiles. And we can then even parallelize the process. So we can run on 20, 50, 100 machines in parallel and process those files really fast. And it was less than 5 days of processing for like a data set that can reach several hundred gigabytes or even terabytes typically. And we did something very similar for the city of Helsinki, including some extra steps. So city of Helsinki is also regularly scanning the whole city with laser scans. So every couple of years, there's a new data set, often with different properties. So the point density increases, we get better quality data every time. The goal in the end for City of Helsinki is to do some vegetation analysis, for example. And we can see on the left side the initial screenshot of our standard classifier, which worked okay, but not great in the beginning. So there were some misclassified roofs. We had very high point density for this data set. So we just added a couple of training samples to optimize the classifier for this data set. And the final result looked really good in comparison. We reached much better accuracies, and we even added some more post-processing steps because that was something that this client was interested in. We wanted to separate low, medium, and high vegetation, and not just do it based on height above ground, but also on a cluster-based approach, so that we can have individual tree clusters and get the whole tree in one class instead of tiling it into 3 different segments. Based on height above ground. And we also added a water shape file. So that's also one of the, let's say, learnings from previous projects. we do not only rely on the AI model, that is one part of a processing workflow, but we can also add either existing data, like we had a very good shapefile for the water bodies, which we can overlay onto the ground layer and use it here, or we can use rule-based corrections or sanity checks at the end to correct parts of common mistakes from the classifier. So that's also part of a workflow. And now I want to share a bit more about the project with Digital Rail Germany. Here we did 2 training iterations for us. It was a completely new use case. It was like data which is not really comparable to a highway scan or a city scan, very new environment. So we started with training data generation. We were still able to do some pre-classification to classify vegetation and ground, but all the new classes needed to be added. And in the initial iteration, we trained on just a few basic classes like the rails, the catenary poles, overhead wires. And in the second iteration, we added more detailed classes to also identify the signals, some fuse boxes or signs along the tracks. And like this, we do this iterative training here as well, adding more edge cases, identifying like issues with the current version, and then adding more. Like also for railway tracks, we have very diverse environments. It can be in urban environments where we have a lot of buildings aside. We have tunnels, we have train stations of all sizes and types. So we need several iterations or a very good training data set in the end to cover all of those use cases and environmental changes to make the classifier work well. And once the classification is done, we can extract specific objects of that, and also this data is used to for the creation of digital HD maps for also supporting autonomous driving on trains, for example. And here again, we also did some post-processing, which is more rule-based, for example, to correct misclassifications within the trees. So that can be done automatically. And you can also see that the rail has 2 colors here on the left. It's purple and blue. The AI classification was both of them, and we actually did a post-processing to just extract the top part of the rail because that is relevant for extracting a vector line or the exact position of a rail. So we first classify the whole rail as it is, and then do a post-processing to just extract the upper part of it. And in this very last part of the presentation, I also want to show a bit how this data can be used in the platform, or how the Pointly platform can assist this process. And I also want to show some more of the rail data, so we can upload all that data to the platform. It will be classified automatically, and then we can work with it. So we can, here in this project overview, we can see the different tiles. So as I mentioned, the data is always split into smaller parts. We can see some preview on the right. We can also see some metadata. For example, this file has 26 million points. And in this example, I want to add some classification. So we have our standard classes, but I now want to also classify some further classes. And as you can see, we can hide or show each individual class. We can hide the points or show them as we like. And all the white points here are unclassified, so those were not objects of interest in the first iteration. So now I'm doing a subselection to classify the vehicles in here. And as they are previously unclassified, we can now add some further classification manually. We can adapt the subselection dynamically. Even within the subselection, we can show or hide the different classes. So I'm hiding vegetation right now. I'm also locking the ground class. That was the second click I've done here. And now I can select the class vehicles, which I added previously. I can select the polygon, and because the ground is locked, I will not override it and only classify the remaining points on top. And just like that, we have classified the 3 cars and 2 bicycles, which are present here. And we have a quite clean classification because the ground was already pre-classified. And now we can hide or show the cars in here, and we could even remove the points on export. So we can do some dynamic cleaning. We can remove noise points or any points which are not interesting after export. So now you have seen this point cloud floating in black space. I also wanted to show that we can add some context by showing the base map. We have implemented OpenStreetMap as well as Open Railway Map, so we can switch to that. Open Railway Map shows also the stations and some connections, and we can also show satellite imagery to give even more contextual information. And the last video I want to show is about the vectorization. So the classification actually supports the vectorization approach in here. The 2 green lines for the rails are already vectorized, and I will add 2 more lines showing the process. So we can select the object that we want to add. I will draw a polyline, and now I will only display the rail points. So also the polyline will only be added or be available on the rail points. So now I can very quickly create the 2 new vectors in here, and showing that together with ground or the rails, or just showing the vectors is already the one output that we can export and use in other tools. So we can export that as GeoJSON and have some extracted rails based on the classification. And in the future, of course, this will also be automated. We have already done some pilots for that. But for now, we have the tools and the platform to do that manually as well. So that's the end of the presentation for now. I'm happy to answer any questions.